Okay, in the last video we got a start on Newton's law of universal gravitation, and I mentioned Kepler's laws of planetary motion, and we need to get into those in a little more detail before proceeding with what Newton did with them. So, Kepler's laws of planetary motion. Now you'll notice that I put the word law in quotation marks. And that's because he made phenomenological observations and he wasn't really predicting anything. And in fact, he actually had 4 laws of planetary motion, although we only teach 3 of them now. I'll go ahead and spoil the 4th one for you. In the 4th one, he found that if you took all the then known planets and made this elaborate construction of spheres, that spherical shells that were nested between between the different platonic solids that were all nested in each other, that the planets could be located on those shells. Near as I can tell, he just got lucky with numbers. The human mind is tricky that way. It's really good at finding patterns even when there aren't patterns to be found. For instance, that's why you can look up at the surface of the moon and see a face in it. There's no actual face there, but your brain is really good at finding patterns. All right. So these were phenomenological observations, and phenomenology is important when you can get to the point where you can at least fit the data to something. That really gives the theoreticians something to go on. And so the first of these laws of planetary motion is the law of ellipses, which says that the orbit of each planet is an ellipse with the sun located at one focus and the other focus vacant. And like I'd mentioned before, this is not a trivial observation. Mars and Mercury, the 2 most eccentric of the planets we've got, basically just look like circles unless you actually impose a coordinate system on them, and then they look like they're off-center circles. And at least to my eye, I can never convince myself that I'm actually looking at an ellipse, but ellipses they are. So anyway, a quick review of the geometry of an ellipse, and forgive what is going to be horrendous art. That's already went better than I could have ever hoped. Okay. So this is an ellipse. The way you make an ellipse is you go ahead and take the 2 foci. Foci is the plural focus, so F and F prime here. Basically, you can just tie a string that attaches these 2 thumbtacks, if you will, stick a pencil in and go around. So in other words, if this distance here is r, and that distance there is r prime, we get that r plus r prime is equal to 2a, where a is this distance right here, which gets called the semi-major axis. So this whole distance here is the major axis of the ellipse. This distance right here is the semi-major axis of the ellipse. Conventionally, this distance b right there is the semi-minor axis. So this whole bit here would be the minor axis. That's the semi-minor axis. Okay. The distance from the center of the ellipse to one of the foci, right so, is related to the semi-major axis. It's equal to epsilon a, where this epsilon is called the eccentricity of the ellipse. And you can find the eccentricity through the the ratio of the semi-minor to the semi-major axes. You can write that the semi-minor axis is equal to 1 minus the eccentricity squared to the 1/2 times the semi-major axis. Okay, if I drop straight down from the focus to the ellipse, this distance right here, usually denoted as alpha, alpha gets called the lattice rectum of the ellipse, and it is equal to 1 minus the eccentricity squared without a square root times the semi-major axis. Then the only other two distances that we really have cause to worry about in our anatomy of the ellipse here will be the distance from the focus to one end and the distance from the focus to the other end. And this one gets called R0, that one gets called R1. R0 is the distance to the pericenter of the ellipse. That is equal to 1 minus epsilon A. And R1 is the distance to the epicenter of the ellipse. That's 1 plus epsilon times A. So a useful construct to remember for another way to think about the eccentricity is you can construct a right triangle like so. Make that the semi-major axis, make this the semi-minor axis, and then this distance right here is epsilon times the semi-major axis. Alright, so that's ellipse anatomy. So Kepler's first law of planetary motion says you put the sun at one of these, you leave the other one empty, sun moves around in an ellipse. Alright, the next one is the law of equal areas. So that one says, and I'm going to greatly exaggerate the ellipse. In fact, I'm going to do it for a comet, just so we can think about it, because we're really getting to the point where I'm lacking clues for how Kepler would be able to pick this out. Anyway, let's imagine we've got a comet way out here, and it's on one of its greatly exaggerated ellipses, which is why we liked it. Here it doesn't really have any tails. When it gets over here, it'll have a dust tail. Like so, and a plasma tail. Like so. Anyway, what the law of equal areas says is if I look at two equal time intervals, I can go ahead and draw a line from the initial to the final position over that interval and note that area. Then on any other part of the ellipse, it will work out that for the same time interval, I'll sweep in the matching area, the areas will be equal. So moral of the story is the comet goes faster at perihelion over here than it does at aphelion over there. Okay, and then finally, the last one, not counting the strange thing with the platonic solids, is his harmonic law. Sometimes called the square cube law. You take the sidereal period in years and square it. That's equal to the semi-major axis in AUs cubed. So he's doing this in very specific units. So sidereal period. And all sidereal means is that you did a 360-degree lap around the sun, as opposed to, say, going between successive alignments of planetary bodies, because those bodies may have moved. This is a semi-major axis. I'm sorry, that first one there's not in AUs, obviously that's in years. This one is in AUs. 1 AU, the astronomical unit, is just the average distance of the Earth to the Sun. Okay, so that's what Newton has to work with. That and his very strong suspicion that this force that's making planets go around the Sun like so is also what makes a rock at the surface of the Earth fall. All right. So if we start with Newton thinking about orbiting the Earth with his cannonball thought experiment, as we now go to think about how Newton found the form of universal gravitation, you can start with the cannonball thought experiment. Immediately from that, you can see that in order to fall around the Earth logically, gravity needs to be isotropic. That means that it's the same regardless of direction, and central. That's just so that you can fall through. Now, the Kepler's second law also requires centrality. So that's the equal areas law. So let's go and knock that one back first. We will start by defining the angular momentum. So that will be L. The angular momentum of any point mass will be its position vector crossed into its linear momentum. And we'll define the torque. And in keeping with your text, and actually most upper division texts, they tend to use N rather than the tau that you usually see in lower division texts. Don't know why. Anyway, it's the position vector from the origin to the point of application of the force crossed into the force itself. All right, so drawing that schematically for angular momentum, there's my origin right there. Let's say here's my mass, it's moving like so, so that's its linear momentum. That would be its position vector. You should convince yourself by the right-hand rule that the angular momentum points into the screen. Similarly for a torque, if a torque were being applied here, if a force were being applied there, then that would be its position vector. You should convince yourself that the torque points into the screen as well. And remember, these angular momenta and torques are always defined with respect to some given origin. Change the origin, you will change them. Okay. So classically, and this is classical mechanics, the time rate of change of the momentum, angular momentum dl dt, will be equal to d dt of r cross p. So you go ahead and do the chain rule, or product rule I should say. So this will be dr dt crossed with p plus r cross dp dt. All right. Well, this gives me v cross p here, and this one gives me r cross f there. Now this v cross p, this is where I'm going classical on you. I'm going to say this is equal to v crossed with mv. Now if I was relativistic, I just have to leave it as a p, or when I go in here, I'd have to put in a gamma. This will be plus r cross f. But notice here, this is m times v cross v. So that just gives me the null vector. And this is the torque. So I end up with that the torque, the net torque on something, is equal to dl dt, the time rate of change of the angular momentum. All right, now if you recall the geometric interpretation of any cross product, so let's say I got a vector A like so and some other vector B like so. I parallel transport them to have common origins. The interpretation of the cross product is that the area here, so if this angle here is phi, this area here will be equal to AB sine phi. So we can interpret the magnitude of the cross product as being equal to the area of the parallelogram that gets defined by A and B. And for what it's worth, A cross B, you should convince yourself, points out of the page. Okay. So now if we look at our swept out area business, so here's a chunk of the orbit right here. So at this moment right there, the linear momentum points like so. If this is differentially long, right, there's my area dA. Well, my displacement dr is going to be equal to the velocity dt, right? So my swept out area dA will be equal to 1/2 of r crossed with dr. So this length here is dr, right? Pointing in the same direction as p. So this will be 1/2 r cross v dt. We can complete the parallelogram here. So there's my other dr there. Complete that back. There, that's the parallelogram. The triangle is half of that parallelogram. Now since P equals mv, I can rewrite this as 1/2m times r cross p. Actually, let me redo it like so. There. So I can divide through by dt. I know I'm not really dividing. So dA dt magnitude will be equal to 1/2m times r cross p. So we can call that a dot, and we usually call that the areal velocity. And I look at this and go, hey, this is 1/2m times the angular momentum. Now, since we want equal areas and equal times, what this really says is we want a double dot to be 0. Well, for that to happen, that implies that L is a constant. And that in turn implies that the torque is 0. Now, the only way that you can have, since the force isn't 0, the only way you can have a 0 torque is if the force law is central. So here I'll make it point away from the center just to prove the point that we can still be a little generic about it. So there's my force there. It could just easily point in the other way, doesn't matter. There's my R. R cross F is 0. So it's either got to point parallel to R, anti-parallel to R. Either way, that is a central force. So Newton deduces that Newton's second law requires a central force, just like the cannonball thought experiment did for orbiting the Earth. Now, just as a side note, long as we're here, let's go and look at our motion here. So there's my origin. So this is some point P here. We're going to end up moving over to Q there. Right. So there is my dr there. So if I break down my dr, and I do this in polar coordinates, this is going to be an r hat times dr, and this will be theta hat times r d theta. So that's my vector dr there. This is the scalar value dr. And then this is theta r d theta. Theta hat, sorry, times r d theta. So following that thought along here, so dA was 1/2 r cross dr. So there'll be 1/2 of r times r hat plus r hat dr. Whoops, sorry, let's try this again. So going over here somewhere, and I don't want the vector sign, my bad. Alright, so then my dA would be 1/2. R is just going to be r hat. And then dr, we worked out, is r hat dr plus theta hat r d theta. And that's not plus, that's cross. Alright, much better. Alright, well, we can evaluate this. We're going to get an r hat cross r hat. That's the null vector. So we're left with an r hat cross theta hat. That's going to be z hat, but it doesn't matter. We're taking the magnitude anyway. So the magnitude of that is just going to be 1. So we're left with 1/2 r times r d theta, or 1/2 r squared d theta. So our aerial velocity, remember, is 1/2 r squared theta dot, so all over 2m. So we can conclude that L is equal to mr squared theta dot. It's a nice little side note there. All right. So the second law requires a central force law. Let's now go and take a look at the first law. And we'll see that that is going to require an inverse square law force. So based on a comparison of freefall data and lunar acceleration data, actually, Newton had a hunch that gravity was inverse square. So he was basing it on some of his own data fit, but Kepler's first law is consistent with that hunch. So let's write Newton's second law here. So m times r double dot, and we're going to make that a vector. This will be equal to some f of r times r hat. That f is a little too, there we go, f of r hat. Oh well, whatever. So this is a scalar function, and the r hat takes care of the fact that it's central. Since it only depends on r, it also makes it isotropic because there's no theta or phi dependence. So this is a central isotropic force. All right, so we can recall from like chapter 1 that r double dot, the vector, is equal to r double dot minus r theta dot squared r hat plus 2r dot theta dot plus r theta double dot theta hat. So we'll take our Newton's second law here and equate the components. So equating the r components gives us m times r double dot minus r theta dot squared equals our f of r. That's equation 1. And then the theta hat components, that gives m times 2r dot theta dot plus r theta double dot equals 0. So that's equation 2. Since equation 2 equals 0, let's play with it first. So equation 2 is telling us that this is mass times, well, if you think about this, this is d dt of r squared theta dot, right? Differentiate that, I'll get 2r dot theta dot plus r theta double dot. All right, so, sorry, not quite. This will be, for what it's worth, m times 2r dot theta dot plus r squared theta double dot equals 0. And that's actually equal to r times equation 2, but whatever, it's equal to 0, right? So the key thing here is that we get that m times r squared theta dot is equal to a constant. So let's call that constant the angular momentum L, because that's what it is. So we'll define a, while we're at it, we'll define a reduced angular momentum, little l, is equal to the angular momentum over m. So we can write r squared theta dot is equal to this little l, which is a constant. All right, now going back to equation 1 here. The usual trick with that guy is to let u equal 1 over r. So then from here we can write that theta dot is equal to L, sorry, from here we can write that theta dot is equal to LU squared. And as we rewrite equation 1, we're going to get, oh, I'm sorry, not yet. So since r is equal to 1 over u, that gives us minus 1 over u, that r dot would be minus 1 over u squared u dot, which is equal to minus 1 over u squared, and then the next cheat we do says du d theta times d theta dt, chain rule. So this becomes minus 1 over u squared du d theta times theta dot. That's cool. So I can rewrite that. R dot is also minus 1 over u squared L u squared theta dot. We just got that from before. So I can write that R dot is minus L du d theta when I equate. All right. So once I've gotten that R dot is minus L du d theta, I can get an expression for R double dot. So there'll be minus L d dt of du d theta. So this is minus L d theta dt d theta of du d theta. So I get minus L theta dot d squared u d theta squared. Putting in for the theta dot, I get minus L times L u squared d squared u d theta squared. So I get that my expression for R double dot is minus L squared u squared d squared u d theta squared. Great. So finally now I can put all that in and rewrite my equation number 1. It becomes m times minus L squared u squared d squared u d theta squared minus 1 over u L u squared squared, whoops, squared there, not there, arg, squared there, not there, equals my f of 1 over u. Now, conventionally, you go ahead and divide through by minus ml squared u squared to get a d squared u d theta squared plus u equals minus 1 over ml squared u squared f of 1 over u. If you want to go back to putting it into terms of r, you could also rewrite that as d squared d theta squared of 1 over r plus 1 over r equals minus r squared over ml squared f of r. Either of these expressions, depending what's more convenient for you at the moment, gets called the differential equation of the orbit. And this is for a particle undergoing a central force. Now, what this gets us is if we somehow know our radius as a function of angle, we can plug it in and get the force law. So as an example, whoops, let's take a look at a logarithmic spiral orbit. So you would write that as r is equal to some constant k times some e to some alpha times theta. So u would be k to the negative 1 e to the minus alpha theta. So plugging into the differential equation of the orbit, differentiating this twice with respect to theta, will give me alpha squared k to the negative 1 e to the minus alpha theta, plus, from this term here, we just say plus u, so we just write that in again, k to the negative 1 e to the minus alpha theta equals, and then, since we ultimately want to get this in terms of r, here I'll use this side of it right here. Minus r squared over ml squared times my unknown f of r. All right, now if I look at this, I recognize this much here as alpha squared over r, and this much here is just plain being 1 over r. So I can solve for my force law. My force law, F of r, will be equal to minus ml squared over r squared times alpha squared over r plus 1 over r. So I can get that as the force law is minus ml squared alpha squared plus 1 times 1 over r cubed. So it turns out that if you've got a trajectory that's moving in that kind of a spiral, it's being caused by an inverse cube law force. So that's all well and good. So we can go ahead and find r of t and theta of t for this force while we're at it. So we remember that r dot minus L du equals minus L du d theta. So that'll be equal to minus L times d theta of 1 over r. And theta dot equals Lu squared. So that's L over r squared. So we get theta dot will be equal to L over k squared e to the minus 2 alpha theta. We can write that as d theta dt, and we can do a little separation of variables action, and so we'll get an e to the 2 alpha theta over 2 alpha is equal to L over k squared dt. All right, so I can integrate both sides. This will just give me e to the 2 alpha theta. Integrating this is going to give me I said e to the 2 alpha theta. What am I doing here? Sorry. I should just have e to the 2 alpha theta, d theta, is equal to L over k squared dt. All right, now integrating, I get e to the 2 alpha theta over 2 alpha will be equal to L over k squared t plus some constant, I'll call it c prime, because I'm going to absorb some crap into the constant. Multiplying through by 2 alpha, I'll get e to the 2 alpha theta is equal to 2 alpha lt over mu k squared plus a different constant. But it doesn't matter because it's just a constant. Then we can take some logs and finally get that theta of t is equal to 1 over 2 alpha times the natural log of 2 alpha lt over mu k squared plus c. And similarly, we can solve for r of t. We had that r dot will be equal to L k to the minus 1 alpha e to the minus alpha theta, so this is equal to L alpha over r. So we can say r dr is equal, because that's dr dt after all, is equal to L alpha dt. So r squared over 2 equals L alpha t plus, we'll call it again c prime, times through by 2. I get r squared is equal to 2L alpha t plus some other constant c, and finally that r is equal to the square root of that. All right. So we just given what as long as we can reason that's a central force, if we know the orbit is a function of theta, we can get the force law, and then we can actually solve for the dynamics of the orbit. All right. So we'll return here to our inverse square law force and see if that meshes with an ellipse. So let's just do that. So elliptical orbit. In this case, r is equal to the latus rectum over 1 plus the eccentricity times the cosine of theta. That's how you write it as a function of theta. So u is equal to 1 plus eccentricity cos theta over latus rectum. All right, so we can differentiate that with respect to theta. Du d theta equals minus epsilon over alpha sine theta, second derivative, is minus epsilon over alpha cos theta. So we can go ahead and put into the differential equation for the orbit. We'll have minus epsilon over alpha cos theta from the second derivative plus 1 over alpha plus epsilon over alpha cos theta. Oh, hey, those cancel. That's nice. Equals, and I'll leave it in terms of r on the other side, minus r squared over ml squared f of r. So we get that f of r is equal to minus ml squared over alpha r squared. So for this to match our GMM over r squared formulation, this requires that L squared over alpha equal GM. That ties between the free fall near the surface of the Earth picture and the planetary motion. But the key thing here is that Kepler's first law requires an inverse square law force. All right, now as for Kepler's third law, we may as well treat that while we're here. It serves as a good check. So we've got our force law. We recall that the aerial velocity we worked out was L over 2m, or the reduced angular momentum over 2. So over one orbit, the aerial velocity times the period would be equal to L over 2 times the period. Well, that's really cool. And we remember that the area of an ellipse is equal to pi AB, which is equal to pi a squared times root 1 minus eccentricity squared. All right, so we can differ. So a dot t will be equal to the area of our ellipse. So this will be pi a squared root 1 minus eccentricity squared. That's equal to L over 2 times the period. All right, let's go ahead and multiply through. We'll go ahead and multiply through by 2, and then we'll square both sides because I feel like it. That'll give me 4 pi squared a to the 4th, 1 minus epsilon squared. That'll equal L squared t squared. All right. But I can peel off one of these a's, because remember that a times 1 minus epsilon squared is the latus rectum. So 4 pi squared a cubed alpha equals L squared t squared or 4 pi squared a cubed equals L squared over alpha t squared. Oh, hey, that's GM. So GM t squared. Awesome. So if I express my, so I can finally rearrange this as t squared equals 4 pi squared over GM a cubed. So apparently, G in units of solar mass year AUs would have to be 1 cubic AU per solar mass square year. Oh, I'm sorry. It's actually 4 pi squared of those. My bad. That gets us Kepler's originally stated harmonic law in those units. You can play with the units and show it actually works. Fun little side note, this is how you actually weigh planets, is you look at things orbiting them and deduce the mass of the thing you orbit. Okay, coming up, we will go and start to take a look at the energetics. Then we will treat the case of nearly circular orbits and scattering.